So application of ordinary differential equations. Ordinary differential equation. This is our switch. Turn down here. T equal to 0. E equal to AM sine omega t. AM sine omega t. So in our example 1, we say the circuit shown below is switched on at t equal to 0. If the circuit was initially dead before switch on, meaning there was no current flowing in that particular circuit at time t equal to 0. Now, before switch on, determine the expression for steady state current flowing in the circuit for time t greater or equal to 0. That means you are supposed to get the expression for steady state current after time t is greater or equal to 0, after the switch has been put on. So in our solution, since this is a circuit, and we would like to relate the voltages, the voltage drop to the EMF in the EMF in that particular circuit. So we say now, applying Kirchhoff's voltage law, applying Kirchhoff's voltage law, applying Kirchhoff's voltage law, applying Kirchhoff's voltage law, we say now, the current that is flowing through this circuit, we are going to call it I as a function of t. So we say Ri plus the voltage drop across an inductor is L di dt. This one should be equated to, this one should be equated to the EMF, which is Em sine omega t, which is Em sine omega t. Now, from this particular expression, this one seems to be a first order differential equation. So we say now, we want the coefficient of di dt to be equal to 1. So we divide it through by L. So dividing through by L, we say this implies what? Di dt plus R over Li is equal to Em over L sine omega t. Now, whatever we are seeing now is a first order linear differential equation, because di dt power 1, I is power 1. All other things remaining are about functions of t. So we say this is in the form, this is in the form di dt plus pi is equal to q. This implies our p is equal to r over l. And q is equal to Em all over L sine omega t. Now, integrating factor. integrating factor will be equal to e power the integral of p dt, which is equals to exponential. The integral of r all over L with respect to t is r over Lt. So our integrating factor is that. Therefore, I, we are solving for I multiplying the integrating factor will be equal to the integral of k, multiplying integrating factor, and we integrate with respect to t. So we say our integrating factor is exponential r all over Lt. Now this will be the integral of k. This will be the integral of k, and our k is Em all over L sine omega t. Now this one is multiplying now exponential r all over Lt. Then we have here the word dt. So that's what we want to integrate and find out. This one will be equal to Em over L, that's a constant, so we take it out here. We have Em all over L. The integral of exponential r all over Lt sine omega t dt. Sine omega t dt. Now, this is, let's call that one I. We would like to know when we integrate that, what are we getting? So, but now, capital I, which is just an integral, I. Not current now. Our current is letter I, small letter I. So I is equal to the integral of e power r all over Lt sine omega t dt. We are going to integrate this one using integration by parts. So we let our u to be equal to sine omega t, and we let our dv to be equal to exponential r all over Lt. So du will be equal to omega cos omega t dt. And our v will be equal to L all over R exponential r all over Lt. So we proceed and we say now, we proceed and back here. We proceed and say this one will be equal to, our I will be equal to uv. So we have L over R exponential r all over Lt sine omega t. Sine omega t minus from integration by parts formula. Minus from integration by parts formula, the integral of v, which is this, L over R over Lt, multiplying du, so omega is here, cos omega t dt, which simplifies to L over R e power r all over lt sine omega t minus omega L all over R, the integral of exponential R all over L t cos omega t dt. This other integral will also clear by integration by parts. By integration by parts. So we say now our I is equals to L all over R exponential R all over LT sine omega t minus omega L all over R, the integral of exponential R all over L t cos omega t dt. Here again we say let u be equal to cos omega t, and let our dv to be equal to exponential R all over LT. So the u will be equal to a negative omega. The u will be equal to a negative omega sine omega t dt. And our v will be equal to L all over R exponential R all over LT exponential R all over LT. So when we substitute, we say our I will be equal to L all over R exponential R all over T sine omega t minus W omega L all over R, omega L over R into UV. U times V, we have L all over R cos omega t. Cos omega t. Then we have minus from integration by parts. And this minus will become positive. And it is now positive. We have the integral. So we have now plus omega L all over R plus omega L all over R exponential. This is the integral, remember, exponential R all over LT sine omega t with a dt, So we close that bracket, which is the same as L over R exponential R all over LT sine omega t minus, we are here, minus omega L squared all over R squared cos omega t. Cos omega t. So this is omega L. This will be a minus. Now all will be here negative terms. This will be a minus. Omega squared L squared. Omega squared L squared. All over R squared. Then the integral of E power R all over L T sine omega t dt. which will give us now. Remember, this is the same as I. So we say it is L over R, A power R all over LT, sine omega t, minus omega L squared all over R squared, cos omega t, plus omega squared L squared all over R squared. Now this is the same as our original capital I. So we can put it here I. This is a minus. So collecting terms with i's together, this is an I. So we say I. We bring this one this side, it will be plus omega squared L squared all over R squared multiplying I, which will be equal to L all over R exponential R all over LT sine omega t minus omega L squared all over R squared multiplying cos omega t. So it can be seen if we make I the subject, it is I into. Now, R squared plus omega squared, L squared all over R squared. This one will be equal to L all over R. L all over R exponential R over LT sine omega t minus omega L squared all over R squared cos omega t. Therefore, our I will be equal to what? Therefore, our I will be equal to what? Our I will then be equal to R squared all over R squared plus omega squared L squared into L over R exponential R over LT sine omega t minus omega L squared all over R squared cos omega t, which will be equal to, let's multiply through by this R squared inside the bracket, and then we bring the exponential out, it will be exponential R all over LT all over R squared plus omega squared L squared into, when we multiply with this, we'll get R. When we multiply here, one R will go, so we'll remain with RL sine omega t. RL sine omega t minus omega L squared cos omega t. So this is our I. Therefore, our I, remember, was equal to, our I was equal to, now I was multiplying e power r all over LT, which was equal to EM over L. EM over L, multiplying that our I, which is now EM over L, and our I, that was the integral. That integral, and our integral is this. It is exponential. R over LT, all over R squared plus omega squared L squared, the whole of this multiplying RL sine omega t minus omega L squared cos omega t. So from this, if we now make I exponential R over LT, this L, we would like it to multiply with it what is inside the bracket. So we are going to, this L, one L will go here and one L will also go there. So we have, this will be equal to EM all over R squared plus omega squared L squared. Now this one multiplying exponential R over LT, R over LT into now R sine omega t minus omega L cos omega t. Now plus a constant of integration, because remember that was an indefinite integral. This is our I. It is an indefinite integral. Then we were supposed to add a constant of integration. So when we make I the subject here, I will be equal to, we divide both sides by exponential R over L multiplying T. So this is EM all over R squared plus omega squared L squared into, because this one will go R sine omega t minus omega L cos omega t plus K. K divided by this, we get KE exponential negative R over L what? T. And that is now the expression of the current. But what was being asked was the expression of what? Expression of steady state current. But there were also some conditions given. We were told when T is equals to 0, I was also equal to 0. So inserting that, we get 0 is equal to T equal to 0, and T is equal to 0. So we have this one is EM all over R squared plus omega squared L squared into, when T is 0, sin 0 is 0. When T is 0, cos 0 is 1. So this is minus omega L. Now plus K. So this implies what? Our K is equal to minus omega L EM is equal to positive. It's a positive that all over R squared plus omega squared L squared. Therefore, our I will be equal to EM equal to Em all over R squared plus omega squared L squared into now R sine omega t minus omega L cos omega t plus K. Our K is omega L plus omega L. It is plus omega L. Em is out here. R squared plus omega squared L squared is also out. So omega L exponential negative R all over L t. So that is the expression for current. So I steady state occurs. I steady state occurs when t approaches infinity. When t approaches infinity. And when t approaches infinity, e power negative infinity is 0. So this term will go. So we say, therefore, I steady state will be equal to Em all over R squared plus omega squared L squared. This one now multiplying R sine omega t minus omega L cos omega t. And that is the expression that was required. This one can also be reduced. You can also be told maybe you put this one in sinusoidal form, where you are supposed to combine this trigonometric term and that trigonometric term to create a single trigonometric sinusoidal function, to create a single sinusoidal function. That one is also possible, and it can be done. So if that one is created, then we can also say now I steady state will be equal to Em all over R squared plus omega squared L squared with the square root. Now multiplying sine omega t minus tan inverse of omega L all over R. So that is the expression that is derived from here up to there, putting the terms in this bracket in a sinusoidal form. So it becomes sine omega t minus sine inverse minus tan inverse omega L all over R. This is an angle which will be treated as a phase angle of the circuit. That's all.